Hello dear students. So, we have stopped our discussion at the virtual temperature. So, just in order to continue, I will say the definition again. So, the virtual temperature is the temperature to which the dry air must be heated so that it acquires the density of moist air, right. So, there are two important aspects here. So, when you heat a gas, its density decreases, right. So, that means in order to reach moist air, you are decreasing the density and you are increasing the temperature. So, that means that the virtual temperature will always be larger than the actual temperature. So, but it gives the provision to accommodate the information of how much amount of moisture is present in the gas without changing the gas constant. That is the beauty of using the virtual temperature, right. Now, so we have already seen how the hydrostatic equation is derived, right. So, hydrostatic equation, just before I introduce what is geopotential, is very important for us to be able to use this expression for the pressure or use this expression as it is, right. Now, the hydrostatic equation or the hydrostatic balance is the simple force balance between the pressure gradient force which allows, which pulls the air to move away from the earth, and the gravity which is holding the atmosphere to the earth. So, these two forces are balanced and then we get what is called as the hydrostatic equation. So, the hydrostatic equation is written as dP by dz. Z is the vertical coordinate, rho is the density, g is the gravity and p is the pressure. So, the rate at which the pressure changes with respect to height is equated with a negative sign between the product of density versus the gravity. Right. So, as a consequence, the pressure at any given point z is equal to integral of g rho dz, right. Now, g is a function of, actually a function of height. That means, g varies as the height increases, but we can pull the g out of this integral and integrate rho versus dz, right. So, this is the basic hydrostatic equation which we will use. So, here we talk about what is called as the geopotential. Geopotential is indicated with a phi. So, geopotential at any point in the Earth's atmosphere, at any height, at any point, is defined as the amount of work that must be done against the Earth's gravitational field to rise a mass of 1 kg from the sea level to that point. So, you are defining geopotential at any given point in the Earth's atmosphere is the amount of work that is to be done in rising an object of unit mass from the surface of the earth to that particular point. So, geopotential now obviously becomes a function of the height. So, at different points, obviously the amount of work that is to be done for rising the object will be different. That means, the geopotential is obviously a function of the height, right. Or in simple words, phi is the gravitational potential energy per unit mass. Simple. You suspend a particular mass at a particular height, the gravitational potential that is held by this object per unit mass is the geopotential. So, units are energy, right, joule per kg, right, gravitational potential energy per unit mass. So, energy per kg, right, joule per kg are the units, right. So, most importantly, so the force in newtons, let us say if you dig in more, the force in newtons acting on 1 kg of mass at a height z above the sea level is numerically equal to g, right. We write the force as F is equals to mg. Now, if I want to calculate force per unit mass, F is simply g, right, in newtons. So, now you have gotten rid of the mass, so which is by mass, force per unit mass, right. Force in newtons on a 1 kg object at a height z is numerically equal to small g, which is the acceleration due to gravity. Now, the work that is done in rising 1 kg of mass from 1 kg of mass from z to z plus dz, work done in rising 1 kg of mass from one particular height z to z plus dz, right. Now, what we have defined is at any given point it is phi from 0 to z, right. So, between 2 points, between z and z plus dz, the change in the geopotential is g dz. That means that the rate at which the geopotential changes with respect to height is equal to the gravity, right. So, we know that from the hydrostatic equation, what is the hydrostatic equation? dP over dz is minus rho g, or 1 by rho dP over dz is equals to minus g, right. This is what we have written here. So, from the hydrostatic equation, 1 by rho dP by dz is equals to minus g. That means alpha dP is equals to minus g dz, because 1 by rho is written as alpha, the specific volume, right. So, if you say, so this is the hydrostatic equation, and a consequence, this is rearranged to be this. So, this is still the hydrostatic equation, but we know that g dz is equal to d phi from this equation, right. So, we use this equation here. So, this is the hydrostatic equation. In the hydrostatic equation, you are making a substitution for dz from d phi. So, d phi is now equals to minus alpha dP, right. So, d phi is equals to minus, so the change in the geopotential is equals to minus alpha dP. So, geopotential phi of z at a height z is thus given by, so what we have done is we just integrated this equation. So, d phi is equals to, so phi is integral minus alpha dP. This is just an integration. So, so the geopotential phi of z at any height z can be given as phi of z is equals to 0 to z g dz. So, we take the geopotential at the sea level to be 0. That means, because we have taken the reference from the sea level, the amount of energy that is spent to rise an object from the sea level to a particular point is the geopotential. So, if you take the reference to be the surface, the amount of energy that should be spent on the surface is 0. We take the geopotential at the surface or the sea level to be 0. So, the geopotential at a height or at a particular point depends only on the height with reference to the surface, but not on the path that has been taken to rise or to reach that particular point. Again, it is very simple. So, geopotential is the amount of energy from 0 to h. So, it does not matter in which direction or in which path you reach this point, the energy is always independent of the path, but dependent only on the height difference between the surface and that particular point. The work done in taking a unit mass of object from a point A with a geopotential phi A to a point B with a potential phi B is the difference in the geopotentials between phi B and phi A. So, you are taking mass from point A to B, you are taking it, but basic thing is phi at a point is defined as z. So, at a point A, the geopotential is already defined to be phi A, the point B is already defined with phi B. So, if you want to take an object from here to here, the amount of energy is simply phi B minus phi A, because phi A is already defined with respect to the ground. So, this information is already there, right. So, we can also define a quantity. So, based on this, we can also define a quantity which is called as the geopotential height, not the geopotential, but the geopotential height. So, geopotential height is when you normalize the energy phi z with respect to the gravity at the surface, at the sea surface. So, z, the geopotential height is defined as the geopotential of at a particular point in comparison to, let us say, g naught or 1 by g naught. Phi of z is defined to be 0 integral of g dz. So, from the hydrostatic balance. So, z is equals to 1 by g naught integral 0 to z g dz, fine. So, phi is the geopotential and z, capital Z, is the geopotential height, right. So, here g naught is the globally averaged acceleration due to gravity at the surface, 9.81 meters per second square. So, this is a standard value, which we take for calculations, right. So, geopotential height is used as the vertical coordinate, right. So, here what is a vertical coordinate? Vertical coordinate is with respect to which you measure the variation of pressure or you measure the variation of density. Vertical coordinate is generally height. So, we take height to be the vertical coordinate against which you draw the pressure like this or you draw the density like this, an exponential decay, that is it. So, what has been realized for specific purposes, height may not serve as a good vertical coordinate. We replace height with density, that means we define pressure surfaces instead of heights. Or, so geopotential, in that way geopotential can also be used as the vertical coordinate, because every point in the vertical direction is unique in the sense that it requires a certain amount of energy to rise a unit mass from the surface to that particular point. And more importantly, this energy does not change if you take a different path, if you take a curved path to reach from the ground to that particular point. So, there is no this dependence of phi over z is single valued, that means we can replace the height with the geopotential, right. So, geopotential height can be used as the vertical coordinate in many atmospheric applications in which energy plays a very important role. So, we take those cases where energy input or output plays a very important role. In those cases, we take geopotential height rather than using the height itself, right. So, let us say, so here a table is given, so where z is the height in kilometers in the base units, let us say in meters or kilometers. So, phi of z, phi of z is this, right. So, if gravity is constant, you take gravity outside. So, this has the dimensions of gravity times the distance, right. Now, you divide by g naught, you have information of height alone, right. So, that has been used in defining the geopotential height like this, and if you use it for defining the vertical coordinate. So, small z is the distance in kilometers and capital Z is again distance in kilometers, but this time this has been normalized with g naught. What is g naught? G naught is 9.81 meters per second square. Now, most importantly, you see, as you increase the height, the geopotential height, which is normalized with respect to surface acceleration due to gravity, is almost the same up till 10 kilometers. I mean, both the height and the geopotential height are almost the same, but they start to deviate after that. This is because how the gravity varies with respect to height, right. So, small z is the altitude in kilometers and capital Z is the geopotential height, right. So, they are same till in the lower atmosphere up to 10 kilometers. After that, they start to deviate, right. So, in meteorological applications or calculations or in theory, we don't, it is generally not convenient to deal with the density of a gas. Let us say if you want to perform some calculations at 100 kilometers, let us say at 15 kilometers in meteorological perspective. So, here generally we always have an empirical relation for calculating the density, how density varies with respect to height. So, we do not know what is the actual value of density at a particular point, but rather we use a crude equation for calculating the density in terms of its scale height and in terms of the density at the surface. Right. So, if you want to have an actual measurement, it is not possible. So, in the geopotential equation, it is very convenient if we eliminate the density. So, geopotential has a density term appearing in it. So, if we eliminate it, it will be more convenient. Right. So, what we do here is we use P is equals to rho RT, the gas equation, and from this we can say that dP by dZ is minus rho g. So, here, so the hydrostatic equation is taken as it is minus rho g and rho is equals to P by RT, right. Now, we use this in the hydrostatic equation, dP by dZ is equals to minus Pg divided by RT, right. Now, again we use not the universal gas constant, but use a dry air's specific gas constant, immediately you should allow the provision of moisture by using virtual temperature, right. So, dP by dz is equals to minus Pg divided by Rd Tv, this is what we have here, right. So, rearranging this expression, so we know that d phi is G dz, right. So, by using this d phi is equals to G dz, that is minus RT times dP over P, right. So, so this is RT by P, RT by P is the density, that is it, right. So, instead of density we are using RT by P. So, that gives a logarithmic term dP over P, Rd times Tv into dP over P. Now, if we integrate now this expression between two geopotential surfaces, let us say phi 1 to phi 2, so we have gotten rid of density, by the way, because we did not wanted density term appearing in the geopotential, we gotten rid of density. So, now the density is now written in terms of the virtual temperature, the specific gas constant of dry air and the pressure itself, right. So, here, so if you assume two geopotential surfaces to be existing, let us say phi 1 and phi 2, what does it mean? It takes different amounts of energy to rise an object of unit mass 1 kg unit mass from the surface 0 or G0 level to these heights. So, the difference of these two energies, of course, I mean these two surfaces should obviously be defined in terms of two pressures, two unique pressures. So, if you integrate from phi 1 to phi 2 is equals to minus Rd times P1 to P2 Tv dP over P, right. Then we have phi 2 minus phi 1 is equals to simple integration. So, I have not pulled temperature Tv out of the integral, that means temperature is now assuming temperature will have some functional dependence in terms of P, I kept it inside. So, Z2, so phi 2 minus phi 1 is equals to minus Rd times P1 to P2 Tv dP over P. So, it is simple. Now, if I divided this with G naught, phi 2 by G naught is Z2, phi 1 by G naught is Z1 is equals to minus Rd by G naught times integral P1 to P2 Tv dP over P. Fine. Right. So, we take this equation forward, right. So, the change or the difference of geopotentials between two pressure surfaces defined with P1 and P2 is Z2 minus Z1 is equals to minus Rd by G naught integral P1 to P2 Tv times dP over P, right. So, Z2 minus Z1 here, Z2 minus Z1 is defined as the geopotential thickness of a layer between pressure surfaces P1 and P2. So, if you take P1 and P2, now see here, most importantly P1, P2 can be used as pressure coordinates. See, height varies linearly, I mean you have 1 kilometer, you have 2 kilometers, you have 3 kilometers like this, right. But pressure does not vary linearly, pressure varies exponentially. So, it gives an additional advantage, an additional information when you use pressure as a vertical coordinates instead of height, because some certain physical phenomena are more dependent on pressure. So, their mechanism can be understood by using pressure as a coordinate. The variation with respect to pressure is more easy to understand. So, pressure can, if the pressure is used as a coordinate, the pressure must be tagged with a certain geopotential. So, the height difference is Z2 minus Z1. So, this Z2 minus Z1 is called as the geopotential thickness of the atmospheric layer which is existing between P1 and P2, right. So, here we have the information of height, we have the information of geopotential height and we have the information of pressure. All these things, they all go hand in hand. We can use any of these as a vertical coordinate, right. So, for an isothermal atmosphere, that means isothermal atmosphere when I say temperature is constant. So, here previously temperature had a pressure term inside. As the pressure changes, the density changes, the mean molecular weight changes and ultimately the virtual temperature also changes, right. So, it is, I mean we have taken the virtual temperature equation sometimes. So, Tv is equals to T by 1 minus epsilon into 1 minus E by P into 1 minus epsilon. Right, this is what we have derived the expression to be. Right, if we just recall that expression, it will be helpful why to define an isothermal atmosphere rather not to work with the temperature variation along with the height. Right. So, here you see Tv is equals to T, the actual temperature divided by 1 minus E by P into 1 minus epsilon. Right. So, here we have defined Tv is equals to T divided by 1 minus E by P into 1 minus epsilon. Right. So, here it makes sense to have Tv inside the integral. Now, if you say that isothermal atmosphere, you no longer variate Tv with respect to height, right. So, we will say that Tv is a constant which we are free to call as T. So, here, so Tv comes out of the integral Rd times T divided by G naught ln. So, you evaluate this integral ln P1 to P2. So, the geopotential thickness of two pressure surfaces P1 and P2 is equals to Z2 minus Z1 is equals to minus RdT divided by G naught ln of P1 by P2. That means now you are able to write P2 with this ln term. P2 is equals to P1 times exponential minus Z2 minus Z1 divided by capital H. What is capital H? Capital H is RT by G naught, which is appearing outside the integral RdT by G naught. Right. So, this is the scale height. So, what have we done? We have taken the geopotential height at a particular pressure surface, and we have taken the geopotential height at a different pressure surface, and we have calculated the difference in the geopotential height between these two pressure surfaces. What we realize is that this expression gives us the variation of pressure with respect to height. But interestingly, we almost have a constant RdT divided by G naught. So, 29.3 times T. So, you take the value of temperature at a particular height, you substitute it inside, you will get the value. So, more importantly, here we define a very important physical parameter which is called as the scale height. So, what is scale height? So, if you see P2 is equals to P1 times exponential minus Z2 minus Z1 by H. So, if Z2 minus Z1 which is in the units of length or the height, right. If it is equals to capital H, you will realize P2 is equals to P1 divided by E. So, scale height is defined as that distance over which the pressure drops to 1 by E-th of its original value, right. So, here R is a constant, T is the temperature, right. So, within a region you define the average temperature to be T. If you know that value of T, your G naught is again a constant. So, you will realize by travelling over a certain distance capital H, the pressure will drop to 1 by E-th of the pressure. This dimension of length is called as the scale height, right. So, I think we will stop here. So, we will continue our discussions about how we can use the hypsometric equation. We have already derived the hypsometric equation in a different class. We will try to see how we can deduce meaningful conclusions based on the understanding of hypsometric equation and the scale height.